Hello and welcome back to the IB Chemistry 2025 TZ2 exam walkthrough. In this video, we'll be doing question 2 of the paper 2 for SL, except HL also has it in common, so also watch this. So this is about thallium, which heavy metal in group 13, irrelevant, just background information. Trivia, if you will. So part A, we're starting off with that 30% of thallium atoms contain 122 neutrons and the remainder 124. So immediately with that information, before we move on, because assuming it's going to become relevant, if 30% contain 122 and the remainder is just going to be 100 minus 30. Okay. And so that's just going to be that 70% have 124 neutrons. Okay. So it says to deduce the nuclear symbol of the isotope of thallium containing 122 neutrons using section 7 of the data booklet. So whenever we have this notation, is you always have obviously the elemental symbol that is right here that's given to you. Meanwhile, up here, you're going to have the mass number, which is going to be the number of neutrons plus protons. And then here is going to be the atomic number, which you can get from the data booklet. It also gives you the number of protons. Okay, so we're going to look up thallium. So TH, not TH, it's like a TI. There you go, there. TL. Why am I just making up letters? Sorry, TL. Oh, bad. So it is the atomic number is up top. And so that is going to be 81. So we're going to have 81 on the bottom here. And then up top, it's not going to be 122. It's going to be 122 plus 81 because it's protons plus neutrons for the mass number. So that is going to be 203. Okay. And so that is going to be part 1. For part 2, it tells us to calculate to 2 decimal places the relative atomic mass of thallium. And it should be noted, once again, that since this is a calculate question, it's purposefully not going to be the same one that is in your periodic table. It's going to be slightly off. Okay. And so we have our 30% of 122 and 70% of 124. And so since for both of these, we're going to calculate the mass number, we already did 203 for 122. So we'll say that we have 30%. I'm going to say TL 203. And then we're going to have 70% of, now we'll just do 81 plus 124. So that'll be TL 205. So thallium 205. And so then we're just going to take a just percentage of this. So we'll do 203 times 0.3. And we'll do plus 205 times 0.7. You could also do times 30 and the 70 and then divide by 100 at the end. That's also an option. But I consider it best to just do it in decimal form. So whenever we do that, we get 203 times 0.3 plus 205 times 0.7. So where we do that, we end up getting 204.4 as our final answer here, but it says to 2 decimal places, so 0. Okay, so that is the correct answer there. I think it is kind of criminal that they put the box here as being so big for such a simple calculation. I genuinely was like second guessing myself whenever I was doing this myself for a second for this exam. I was like, wait, why is this box so big? I was really confused. So this third part is going to be explain why in terms of nuclear charge and the shielding of the valence electron. That's new. Normally, they don't get that specific in the question. So, like, people have been missing this one? I don't know. Normally, you just have to know that. But anyways, in terms of those two things, the first ionization energy of thallium is lower than that of lead. Okay, so you kind of just have to compare the nuclear charge and the shielding. Okay, and so the nuclear charge is just the number of protons. Okay, and the shielding is going to be based on the period number. Okay, and so this is based on that of lead. Lead is PB. It's not like LD, it's just PB. Okay, so we're going to find both of those in our data booklet. So we have thallium and we have lead. And so since they're in the same period 6, they're going to have the same shielding. Okay, obviously, if this were an actual exam, as I would put thallium and lead have the same shielding. I'm going to write it down short form here, just so not wasting time. So I'm just going to put same shielding, but in terms of their nuclear charge, lead has a higher nuclear charge, but PB has a higher nuke charge. Okay. And so essentially, what that means is that because it has a higher nuclear charge, the protons that are in the nucleus, they are more positively charged. There's more of that positive charge. Ionization energy is just the ionization of one electron. Okay. So whenever you have more positive charge in the nucleus, it's like you have more, like, hey, don't go. More whispers of the nucleus going, don't go, because it's positive, and it's very attracted to that negative electron. And so that negative electron is like, wait, I don't want to go. And so it's harder to ionize it. And therefore, the ionization energy is higher. Okay. Meanwhile, with thallium, it has a lower nuclear charge. Okay. Therefore, the whispers of the nucleus are a bit less. They're like, oh, maybe don't go. But so the electron's like, oh, no, I'm gonna dip. And so it's a lot easier to ionize that electron, and therefore it has a lower first ionization energy. Okay. And so that would be what you would say kind of there. Okay, it's the same shielding, but higher nuclear charge. You don't have to get too specific from what I'm aware of in terms of how that nuclear charge, in terms of the theory, affects the ionization energy. Okay, like you don't have to really go too deep into it, so you don't have to put as much detail here. Okay, and so that is going to be that first part of this question. Cool. So this part B of this question 2 is that thallium sulfate has the formula of TL2SO4. And so immediately kind of what this is telling us is the charge on thallium. So yeah. And so this SO4 is 2 minus. Meanwhile, thallium is going to be +1 because the subscript of SO4 is 1. There's only one of them. That means that has to be the charge because the crisscross. Because normally you go crisscross, we can reverse by going boom. Okay. Or what I can also do sometimes is I can put, okay, the subscripts are 2 to 1. So that means that the charge is the opposite ratio of 1 to 2. So SO4, 2 minus, that matches. Meanwhile, thallium TL would be +1. Okay. So that is an option. So just noting that immediately. For this part 1, as it says it contains ionic and covalent bonds. This is true because the TL and SO4 are both ionically bonded because they're both ions. But within the polyatomic ion, there is covalent bonds. Okay. And so this is saying the state which particles are joined by the covalent, which ones are ionic. Okay. So our ionic is going to be between the TL plus and the SO4 2 minus. Meanwhile, the covalent bond is going to be between the sulfur atoms and oxygen atoms in the SO4 2 minus, because the polyatomic ions, they are an ion overall, but within the ion, there is those covalent bonds. Okay. So oxygen, I'm going to put atoms. Okay, boom. Then it says to contrast covalent and ionic bonds based on their valence electron interactions. This one is quite nice because normally it says to describe the bonding like ionic or covalent, and you have to use this really oddly specific wording from the subject guide, like, oh, electrostatic attraction between oppositely charged cations and anions, right? But with this one, when saying just the valence electron interactions, is it's actually what you usually want to say. Is all you have to do is just say that, oh, those valence electrons in the covalent bonds are shared. Those valence electrons are shared between the two atoms that are in the bond. Meanwhile, with the ionic bonds, there is the complete transfer of valence electrons. Once again, should be noted that I am not using the full writing that I would put on my own actual exam, as I would actually put what I'm more verbally saying. I just don't want to write that because then I'm just writing for an awkward amount of time while being silent. Anyways, So 4, that is that one. Very simple. I actually second guessed myself when I was doing this exam myself. I was like, is that right? That feels too simple. No, it's right. For this part 3 is to write an equation for producing thallium sulfate. So once again, that is that TL. God, why do I keep putting TI? TL2SO4 from by reacting. And so that's going to be our producing. So it's going to be our product by reacting solid thallium hydroxide. So this is where we have thallium plus OH minus. So they're going to combine in a 1-to-1 ratio to make TLOH solid with sulfuric acid. So that's going to be our H2SO4. You should just have that memorized from knowing the polyatomic ion of sulfate. Okay. So this is where those two are going to be our reactants because it says from, right? And so we're going to have our TLOH solid reacting with our H2SO4 AQ to then form TL2SO4 AQ. We're going to assume that it's just aqueous here. I don't think we have to. Yeah, because this is a solution. So we can assume that that is aqueous there. Okay. And so whenever we're looking at this so this is a hydroxide and an acid forming the salt. And so since this is a neutralization reaction, we're also going to form water. And also we know this because in our reactants, we have H2. If we just had TL2SO4, we would not have any hydrogens on our products and we could not balance our equation. So that's how we know we have to have water. And also just knowing that in our neutralization reactions, we have hydroxide plus acid forms salt plus water. That's one of the big 3 types of acid-base reactions, including the ones with like carbonates, carbon dioxide, water, salt, as well as like our metal acid, H2 gas. You should know those, okay? And so I'm going to put that also as a liquid. And then we're just going to make sure this is balanced. It could already be, who knows? So we see that our thallium, we have 2 on this side, and we only have 1 over here. So we're going to make this 2. Boom. Okay, let's check out our sulfurs. Is we have 1 over here and also 1 over here. So that matches. Our oxygens is we have 4 plus 5, 6 over here. And then we have 4 plus 5. So we're going to make this 2 to make that 6. And then our hydrogens should ideally be balanced by this point, but we have 2, 3, 4. And then we have 4 also over here. So now that is balanced. It does not explicitly say to balance the equation. However, that is always a step that is assumed that you have to do in this. That is always the beginning of every mark scheme, that every equation should be balanced. Then this last one, this part 4, is to calculate the volume of 2 mole per decimeters cubed sulfuric acid required to react completely with 10 grams of thallium hydroxide. And so what we need to do here is we have this balanced equation up here. And so I always like to make a plan first before we do anything. So we're going to have to go from grams of our thallium hydroxide to our moles of thallium hydroxide by using the molar mass, which we can calculate from the periodic table. And then we're going to need to go to moles of our sulfuric acid that is required using the ratio from the balanced equation. We're just doing some dimensional analysis here, canceling out our units. And then we need to go to our volume decimeters cubed of our H2SO4 using our concentration that we are given. Okay, to just cancel out our units until we get what we want. So we're starting off with our 10 grams of TLOH. And so times, we're going to divide by the molar mass. Our thallium has a molar mass of 204.38. So 204.38 plus oxygen 16 plus 1.01. So that ends up getting us 204.38 plus 16 plus 1.01 gives us this 221.39 grams of TLOH per 1 mole of TLOH. We're going to go to our balanced equation. And so we need TLOH on the bottom. So what we're canceling out. So that's going to be 2. So 2 mole TLOH. And then sulfuric acid is going to be on the top because that's what we want, our unit that we're converting to. So that's going to be 1. Okay. And so then finally, we're going to put this down here, but you can visualize it next to it, is we need to go to our concentration. And so our concentration is in moles per decimeters cubed. So 2 mole is we want 2 mole to be in the denominator in order to cancel out this 1 mole. Okay, so we're going to divide by our concentration. So we're going to divide by our 2 mole of H2SO4 per 1 decimeters cubed H2SO4. I like to always do it as once rather than calculating each intermediate. And so that's going to give us 10 divided by 221.39 divided by 2, and then divided by 2 again. And so that's going to give us 0.0. We initially have 3 sig figs, so 113 decimeters cubed of sulfuric acid. And that is the correct answer for that one. So that is question 2, just using some nice dimensional analysis skills. Okay, and it seems like a really small number, but it's actually right, I swear. I also second guessed that, but it's correct. Psych, I got you. Psych. You thought this question was over. I actually did too, and then I turned the page. Oops, there's 2 more parts. So this video is going to be longer than I expected. Anyways, part 5 is to predict whether or not thallium hydroxide is amphoteric, considering the position of thallium in the periodic table. So this is where we just need to remember what the heck amphoteric means, which is essentially that something can act as either an acid or a base. And so the main example of amphoteric oxides, hydroxides, whatever that we know is aluminum. Aluminum is our boy here, okay? And so that is because it is in period 13, not period, group 13, my bad. Group 13, okay? And so it's essentially right on that edge to where it's kind of in the middle of that trend of the acid base oxides trend. Okay, and so if you look at thallium, it happens to be in the same group as 13. Is that enough to be evidence that it might be amphoteric? Well, let's just predict. So, yeah, that is exactly what they're looking for. So you would say yes, because in same group as aluminum. I don't know how I spelled that. Aluminum, which is amphoteric. I don't want to write all out amphoteric, so we're gonna leave it there. Okay, so that would be that one. It's very simple. Meanwhile, so lots of that's also where we need to remember the periodic table, and it's grouped in a certain way because of that. Things that are in the same group or period tend to show the same trends. Very useful for a lot of things, including formal charge. Sorry, a little sidetrack, but it's very useful because, like, when drawing Lewis structures, like nitrogen, phosphorus is in the same groups. You can just pretend it's nitrogen in any Lewis structure because it acts the same. Same thing with sulfur and oxygen, except for when it has an expanded octet. Anyway, sidetrack over. This part 6, discuss how the relative reactivity of copper and thallium could be established using metals and aqueous solutions of their sulfates. This is something where you'd be like, it's just you have these 2 things, react them together. If they react, then one is more reactive than the other. Okay, so this is a very common experiment where it's just displacement reactions. All of the redox questions start off with some hypothetical displacement reaction, right? And so what you would do essentially is you would have copper and aqueous thallium sulfate, and you may be like, that's like just reacting them, that's only one thing. And this is 2 marks. What's another mark? Where it says discuss. And so it says the relative reactivity could be established. You need to say what the results would be, essentially. That is M2. Okay, a lot of people forget that. And so you have some copper and some aqueous thallium sulfate. And so essentially is that if you get copper sulfate, That essentially means that copper went from copper solid, which has an oxidation state of 0, to copper sulfate, which has an oxidation state of 2 plus. And so if that reaction occurs and you get copper sulfate, that means that copper was oxidized and therefore it's more reactive. Because remember, reactivity is just which is more likely to be oxidized. More reactive or likely to be oxidized. Those are the same thing. Okay, so if get copper sulfate, copper more reactive. Okay. You could also do the opposite of this. That also would work. You could say that you had thallium and then aqueous copper sulfate. And if you got aqueous thallium sulfate, then that would mean that thallium was more reactive. You could do either one. Either one would tell you the trend. Okay. And so that is now actually the end of question 2. And now I have to re edit this video and re upload it because I already attempted to. Kill me. Okay.